Hi everyone, my name is Thiago and I am a PhD student at the University of São Paulo. And for this small seminar, I will talk about the thermodynamic formalism on generalized configuration spaces with countable state, which is a work I have been developing jointly with Rodrigo Bissacco, Rui Axel, and Rodrigo Frauzino. Before we in fact start the talk, I have some disclaimers to make. The first one is to tell you that this project is actually in the interface area between the C-star algebras, dynamical systems, and probability theory. And I will be focusing specifically in this talk, the dynamicist and probabilistic part. But if you are interested to the algebraic side of this work, I recommend you to watch the Rui Axel's talk at ICM 2018. And for more detailed explanation about the dynamical part, I recommend the Rodrigo Bissacco's talk on the Zoominar in the dynamical systems at the University of Porto. And the last disclaimer I have to make is that we will be assuming that the audience is familiar with Markov shift space. At first, we introduce the generalized Markov shift space. Every configuration in this space is basically an element of the 0,1 power f space endowed with the product topology. Given a configuration C and word nef, we say G, we say that C is filled on G if its canonical projection is 1. And further, we consider the subspace of 0,1 power f as being the set of configurations which satisfies the rules which are in the screen. In particular, we mentioned that configuration is said to be connected if for every 2 words which C is filled on them, the whole path between these 2 words in the Cayley tree is also filled. The current picture shows how the elements of the free group are encoded in the Cayley tree. Every word in the free group corresponds to a vertex in the Cayley tree, and the oriented edges corresponds to the multiplication by an element of the generator set, which is in our case the alphabet. The next picture shows how we realize the 4th rule. Now we show how the standard Markov shift space can be included into omega A tau. So take any element omega in sigma A and define the following configuration as we state here. C is filled on E and it's also filled in any finite subword of omega, and the remaining words can be determined uniquely by the 4th rule. So now, since we have sigma A included into omega A tau, we can define the generalized Markov shift space just by taking the closure of sigma A on omega A tau. Now we present some very interesting properties of this generalized space. In general, this space is locally compact. But even in cases where sigma A is not locally compact, we can have that XA is compact. For example, when the transition matrix has a full row of 1s. Also, in the locally compact case, we have that these 2 spaces coincide, and the inclusion of sigma A into XA is continuous and preserves the Borel structure. By Borel structure, I mean that every Borel set of sigma A is a Borel set of XA. So we have the compatibility of Borel measures between these 2 spaces. Of course, I have by definition that sigma A is dense in XA. However, its complement, when it's not empty, which we call epsilon A, is also dense in XA. Finally, we we observe that the shift action extended to this space is basically a coordinate translation. However, this cannot be defined in the whole space. Now introduce the thermodynamic formalism for this space. Here, U will be the domain of the shift map, and D will be the exponential of beta F, where F is the potential of the model. For every A Borel set which is contained in U, we call it special when its restriction to the shift action is injective. A Borel measure in XA is said to be deconformal in the sense of Peterson when the equation 1 is satisfied for every spatial set A. We'll be presenting here two main examples. The first one is the Renewal shift, which both transition matrix and symbolic graph are presented in the screen. Epsilon A corresponds to the finite words ending in 1 plus a configuration called the empty stem configuration. This is the stem representation, which is basically the longest path of positive words in the calligraph which are filled in the configuration. The current picture represents one configuration of the epsilon A set, and this box, which is written C0 minus E1, corresponds to the empty configuration, which we present further. And this is the stem of the configuration, and you see this is the longest positive path. Alternatively, you can just use the last one, or if it is infinite, the corresponding element of the Markov standard shift. And this is how the shift action acts in this space. So as you can see, it just translated to behind in the past in the direction to the element E. As you can see, we just cut off the first coordinate and go back in the past. And this is what I was talking about, the empty stem configuration. And as you can see, these blue dots are basically the elements of the free group. For the renewal shift, we present basically two results, which correspond to the existence of new conformal measures which are not detected in the classical theory. The first one is just a existence result. For example, if you have a potential which is bounded away from 0, we have the existence for some beta values of beta of a unique beta F conformal probability measure that vanishes in the classical setting. And also we have, as you can see, some results about the absence of such measures. Maybe one of the most interesting results is when you take the potential constant equals to 1, and you are able to find a critical value of beta, which we call beta C. In this case, is log 2, such that for beta greater than beta C, we have a unique E beta conformal probability measure that vanishes on the classical Markov shift. And for smaller values of beta than beta C, we have the absence of such measures. More than that, these measures are connected to the classical framework in the sense that if you take beta to the limit of beta going to beta C, you have that these measures converges in the weak topology to the to me beta critical, which is the classical one, and it was studied by Sari, and explicitly this measure is the one you can see here in the screen. And this brackets in alpha actually corresponds to the cylinder sets the classical cylinder set. And the next result is about slightly modification in the Renewal shift, which we call pair Renewal shift. And when we add a second infinite emitter in the symbolic graph, in this case, we have actually two empty state configurations, which are the one you can see in the screen. And which is more interesting that you can divide the epsilon A set into two disjoint families, which makes it a partition of the set, and each partition corresponds to empty configuration, and you have also the existence and the absence, similar to the Renewal shift, of extremal conformal measures, as you can see in the screen. And the conditions are quite similar to the Renewal shift. And in particular, for the constant potential equals to 1, we have for beta greater than log 3, the existence of two extremal conformal measures, and in particular, we have a finite set of conformal measures, since the convex combination of conformal measures are also conformal measures. And for beta smaller than log 2, we have the absence of such measures. These are the main references of this work. The focus of this talk is the one in red, and there's another one in dark red, which is another work where we have been working on the case of DLR measures, which corresponds to the Gibbs measures in statistical mechanics. These are also some more references of our work. Thank you for the opportunity, and stay safe from COVID-19.